Every single node database eventually hits a physical wall. The CPU and disk I/O can only process so much incoming data before the hardware fails. To get past that limit, we need to design a distributed key-value store. And for this specific architecture, we are optimizing for strict accuracy over raw scale. The CAP theorem dictates that we cannot have perfect consistency, perfect availability, and partition tolerance all at once. Here, we are aggressively prioritizing durability and strong consistency. If the system faces a catastrophic error, it will stall a request rather than return bad data. The engineering challenge is distributing data across thousands of independent servers without relying on centralized locks. Locking rows or tables across a network introduces latency that destroys performance. Solving this requires physically separating the components. We have to decouple the layer that actually stores the data from the layer that routes traffic and tracks cluster state. Once those are separated, maintaining strong consistency across a lockless cluster requires deterministic mechanisms, specifically global sequencers and strict quorum rules. By combining decoupled routing with deterministic conflict resolution, we can build a database capable of handling unbounded data growth, while mathematically guaranteeing the accuracy of every read and write. Scale begins with redundancy. We organize servers into odd-numbered clusters called replication groups. Exactly one node is elected leader, handling every single request to guarantee consistency. When a write arrives, it is appended to a persistent disk log before pushing to an in-memory index. Writing to an append-only log is computationally cheap, sustaining massive throughput. But the leader can't confirm the write yet. It broadcasts the data to its followers. Once a majority successfully writes to their logs, the leader returns a success signal to the client. This quorum ensures that if a hardware failure occurs milliseconds after a successful write, the data survives on a replica without ever sacrificing the strong consistency of the overall system. At millions of operations per second, a distributed system lacks a centralized global clock. This means two clients might try to write to the exact same key simultaneously. Resolving these collisions using traditional table-level or row-level locks across a network would freeze the cluster and bottleneck performance. Instead of locks, every record receives a 16-byte sequencer, combining a timestamp, node ID, and loop counter into an increasing integer. If two simultaneous put requests hit the same key, both are allowed through, each assigned its own unique sequencer number. The logic requires no network locks. The system compares the two sequencers, enforcing a last write wins rule. The higher integer value is kept, and the other is simply discarded. This deterministic sequencer acts as a lockless, mathematical referee, allowing the cluster to process massive parallel throughput while strictly maintaining the correct order of operations. A single replication group is physically constrained, eventually hitting a storage limit of 5 terabytes or maxing out its input-output capacity. Expanding beyond this requires horizontal scaling. This control plane map shows client requests hitting a load balancer, distributing traffic to stateless request managers. To organize this, a centralized metadata manager is added. It acts as the source of truth, mapping the stocks table directly to replication group 1. To prevent the metadata manager from becoming a read bottleneck on every query, the request managers cache this map locally in their own memory. When a client requests a key, the request manager instantly consults its local memory, identifying the correct leader and routing the operation directly to it. Isolating state tracking from high-volume traffic routing allows the system to seamlessly direct millions of operations across thousands of independent storage nodes. As data grows, specific datasets become hot tables. If a table experiences explosive growth, it threatens to overwhelm its assigned replication group. To avoid going offline, the controller logically slices the hot stocks table between keys C and D. It creates a new replication group 2, instructing group 1 to reject new writes for keys A through C, routing them instead to group 2. Historical data is copied to group 2 in the background. During this, GET requests query both groups simultaneously. The request manager compares the two returning packets, passing only the one with the higher sequence number to the client. Once the copy finishes, Group 2 takes full ownership, and queries resume to a single group. Dynamic sharding with dual reads enables the database to infinitely balance hardware loads and scale horizontally, all without dropping a single client request. To prove this architecture works, we have to look at how it handles a network partition. In this scenario, a jagged line represents a partition isolating the leader of a replication group from the metadata manager, though it remains tethered to a client request. Detecting a missed heartbeat from the isolated leader, the metadata manager legally elects a new leader from the remaining connected nodes in the group. This creates a split brain danger. The old leader is cut off, unaware of its demotion, and attempts to process a new incoming put request from its connected client. The system defends itself through quorum. When the old leader attempts to send the right to the followers, they consult their updated metadata state and return large red X's, blocking the operation entirely. The old leader fails to achieve a majority and outright rejects the client's request. By explicitly stalling the isolated client and sacrificing availability, the system mathematically guarantees that split-brain data corruption is impossible. The architecture rests on treating these strongly consistent 5-terabyte replication groups as modular atomic units of storage. The control plane stitches these isolated atomic units together, using stateless request managers and dynamic table splitting to route traffic seamlessly across the hardware. A deployment of 100 replication groups yields 500 terabytes of perfectly consistent data. Stepping up to 10,000 replication groups yields 50 petabytes of storage. Every single byte operates with the exact same durability guarantees as a single machine. By decoupling cluster state from traffic routing and replacing network locks with deterministic sequencers, engineers can build a database that scales linearly alongside the raw demands of the modern internet.